good day, everyone. We are the Group 2 and we will report about the Chapter 43, the Nuclear Physics. So, watch the video and we hope that you will learn something from it.
So, learning goes. In this topic, we will learn some key properties of atomic nuclei and how the binding energy of a nucleus depends on the numbers of protons and not neutrons that it contains. And also, we will learn the most important in ways in which unstable nuclei undergo radioactive decay and how the decay rate of radioactive substance depends on time. Also, we will learn some of the biological hazard and medical uses of radiation and how to analyze some important types of nuclear reaction and the sequence of nuclear reaction that allow the suns and the stars to shine. So the first topic here is the properties of nuclei. So the nucleus is Rutherford found out that nucleus is tens of thousands of times smaller in radius than the atom itself. Its scattering experiments showed that we can model a nucleus as a sphere with a radius that depends on the total number of nucleons, number of protons and neutrons in the nucleus. So nucleon are also the mass number because it is the nearest whole number to the mass of the nucleus measured in unified atomic mass unit. So this is a constant value. One mass unit is equal to 1.6605387882 by 10 raised to the power of negative 27 kilograms. So in the nuclear density, the volume of the sphere is in a constant value of 4 pi constant radius by raised to the power of 3 by 3. So in example 43.1, calculating the nuclear properties, the most common kind of ion nucleus has a mass number of A. Uh, A is the nuclear number, is equal to 56. So we have to find the radius, approximate mass, and approximate density of the nucleus. So solution, uh, in the equation, it tells us how the nuclear radius depends on the mass number of the nuclear number. The mass of the nucleus in atomic mass units is approximately equal to the value of the nuclear number, and the um, density proton is mass divided by volume. So in executing, the radius and approximate mass are in the constant value of radius is equal to radius 0 nuclear number by raised to the power 1/3 and is equal to uh, 1.2 by 10 raised to the power of negative 15 m, and the 56 is the nucleon number, the nuclear number, then 1/3, then this is equal to 4.6 by 10 raised to the power of negative 15 m, and it equal to 4.6 fm. So the mass so uh, the mass is approximately equal to 56 mass units by 1.66 uh, by 10 raised to the power of 27 negative 27 kilograms mass units, and it is equal to 9.3 by 10 raised to the power of negative 26 kilograms. So the volume of the nucleus, which we treat as a sphere of radius, and its density protons are the volume, is equal to 4/3 pi constant radius cube, and is equal to 4/3 pi constant radius 0 cube nucleon number, the A, and is equal to 4/3 pi constant 4.6 by 10 raised to the power of negative 15 m cube, and this is equal to 4.1 by 10 raised to the power of negative 43 m cubed. So the proton here is equal to mass over volume, and approximately equal to 9.3 by 10 raised to the power of negative 26 kilograms over 4.1 by 10 raised to the power of negative 43 m cubed, and this is all equal to 2.3 by 10 raised to the power 17 kilograms m cubed. So, as we mentioned above, all nuclei have approximately the same density. The density of solid iron is about 7,000 kilograms mass mass m cube. The iron nucleus is more than 10 10 raised to the power 13 times as dense as iron in the bulk. Such densities are also found in the neutron stars, which are similar to the gigantic nuclei made almost entirely of neutron. So, a 1 centimeter cube of a material with this density would have a mass of 2.3 by 10 raised to the power 11 kilograms or 230 million metric tons. So our next topic is the nuclides and isotopes. So building blocks of nucleus are the proton and the neutron. Neutral atoms. Nucleus is surrounded by one electron for every proton in the nucleus. Single nuclear species having specific values of both Z and N is called nuclide. Some elements have nuclides that have the same Z but different N. These are called isotopes. So in the proton, proton mass is equal to 1.007276 mass unit, and is equal to 1.672622 by 10 raised to the power of negative 27 kilograms. The mass, neutron mass, is equal to 1.008665 mass unit, and is equal to 1.64927 by 10 raised to the power of negative 27 kilograms. The electron mass is equal to 0.00054858 mass units, and is equal to 9.10938 by 10 raised to the power of negative 31 kilograms. So isotope symbols. So the A here is the mass number, which is the number of protons add up to the number of neutrons. The X here is the element, and the atomic number here is the letter Z, or the number of protons. So for example, a magnesium. So Mg is the element, then the atomic number of magnesium is 12, then its mass number will be 24. So in magnesium, number of protons is 12, then electrons and having 12 electrons and having 12 neutrons. So next topic is the nuclear spins and magnetic moments. So like electron, protons, and neutrons are also spin negative 1/2 particle with a spin angular momentum. So the total angular momentum of the nucleus is the vector sum of the individual spin and orbital angular momenta of all the nucleons. When the total number of nucleons is even, nucleon spin is an integer. When it is odd, this odd nuclear spin is a half integer. The total nuclear angular momentum quantum number is usually called the nuclear spin. So, associated with nuclear angular momentum is a magnetic moment. So, we have here an example for 3.2 proton spin flips. Protons are placed in a 2.30 T magnetic field that points in the positive Z direction. So, in A, what is the energy difference between states with the Z component of proton spin angular momentum parallel and anti-parallel to the field? B, a proton can make a transition from one of the states of the other by emitting or absorbing a photon with an appropriate energy. Find the frequency and wavelength of such proton. So in the solution, the proton is in a spin of negative 1/2 particle with a magnetic moment uh, in the same direction and as its spin angular momentum. So its energy depends on the orientation of its spin relative to an applied magnetic field. If the z component of the spin angular momentum is aligned with external magnetic field, then the magnetic mass is equal to the positive value given in equation. If the z component of spin angular momentum is opposite by external magnetic field, then the magnetic mass is the negative of this value. The interaction energy in either case is mass unit and equal to negative magnetic mass uh, magnetic field. The difference between these energies is our target variable in part A. So we find the photon frequency and wavelength using E is equal to HF and A is equal to HC. HC constant. So in executing, when the z components of spin angular momentum and spin magnetic moment are parallel to external magnetic field, the interaction energy is mass unit equal to magnetic mass by the magnetic field. So this is equal to negative by 2.7928 by 3.152 multiplied by 10 raised to the power of negative 8 electron volume T. So you have here the magnetic field points, the 2.30 T, and this is all equal to negative 2.025 by 10 raised to the power negative 27 electron volume. When the z components of spin angular momentum and spin magnetic moment are anti-parallel to the field, the energy is positive 2.025 by 10 raised to the power negative 27 electron volume. Hence, the energy difference between the state is delta E is equal to 2 by 2.025 times 10 raised to the power negative 27 electron volume is equal to 4.05 by 10 raised to the power of negative 7 electron volume. So in the B, the corresponding photon frequency and wavelength are F is equal to delta E by H over H, and is equal to 4.05 by 10 raised to the power of negative 27 electron volume over 4.136 multiplied by 10 raised to the power of negative 15 electron volume by spin. So F is the frequency, so this is equal to F I equal to 9.79 by 10 raised to the power of Z raised to the power of 7 Z, and is equal to 97.9 mHz. So this is the frequency and the wavelength. So in delta, the K delta is equal to CF, C over the frequency, C over the frequency equal to 3.00 by 10 raised to the power of 8 uh, uh, m m since and over 9.79 times 10 raised to the power of 7 as negative raised to the power as 1 equal to 3.06 m. This frequency is in the middle of FM radio band when the hydrogen specimen is placed in a 2.30 magnetic field and radiated with radio waves of this frequency. Proton spin flips can be detected by the absorption of energy from the radiation. So the next topic is the nuclear magnetic resonance, and MRI. So spin flip experiment of the sort are called nuclear magnetic resonance, or NMR. It had been carried out with many different nuclides. An elaboration of this basic idea leads to magnetic resonance imaging, or the MRI, non-invasive imaging technique that discriminates among various body tissues on the basis of differing environments of protons in the tissues. So we have here an images, which is the MRI, the movement of MRI. So in the image A, the random spin of hydrogen proton. So protons, the nuclei of hydrogen atom in the tissue under study, normally have random spin orientation. In the external magnetic field, in the presence of a strong magnetic field, the spins become aligned with a component parallel to external magnetic field. A brief radio signal causes the spin to flip orientation. Then, as the proton realign with the magnetic field, they emit radio waves that are picked up by sensitive detectors. In the image B, since the external magnetic field has a different value at different location in the tissue, the radio waves from different location have different frequencies. This makes it possible to construct an image. In the image C, an electromagnet used for MRI. So this machine is used usually in the hospitals. So in the upper part, we have the main coil supplies uniform for the magnetic field. Then at the center part, we have the X coil various magnetic field from left to right. Then Z coil varies magnetic field from head to toe. Then Y coil varies magnetic field from top to bottom. Then transceiver sends and receives signals that creates an image. This center part, this creates an image. So next one is the nuclear binding and nuclear structure. The energy must be added to the nucleus to separate it into its individual protons and neutrons. The total mass of the nucleons is always greater than the mass of nucleus by an amount called mass defect. So in example 43.3, the most strongly bound nuclei, find the mass defect. So we have to find the mass defect, the total binding energy, and the binding energy per nucleon of nickel, then having a um, mass number of 62 and a atomic number of 28. So which has the highest binding energy per nucleon of all nuclides. So the neutral atomic mass of nickel is 61.928349 mass units. So the solution, the mass defect is delta mass is the difference between the mass of the nucleus and the combined mass of its constituent nucleons. The binding energy E B is this quantity quantity multiplied by C squared, and the binding energy per nucleon is EB divided by the mass number on the nucleon number. We use the equation for 3.10. So mass number delta mass is equal to ZMH and added up by NM. So the ZMH is the Z protons plus Z electrons, and and the EB is the binding energy, and it's added up to and added up to NMN minus the mass of the neutral atom to determine both of the mass defect and the binding energy. So to execute with the Z is equal to 28 and MH is equal to 1.007825 mass unit. The N is equal to the nucleon number minus a Z is equal to 62 minus minus 28. So 62 is the mass number. 62 is the mass number. Mass number minus 28. 28 is the atomic number of the nickel, and is equal to 34. Nm is the neutron the neutron mass is equal to 1.008665 mass unit, and mass of neutral atom is equal to 61.928349 mass units. So in the equation, this gives delta mass equal to 0.585361 mass units, and the binding energy is then binding energy is equal to 0.585361 mass units by 9 31.5 mass electron volume by mass units, and this is equal to 545.3 mass electron volume. So the binding energy per nucleon is uh, binding is AB by um, uh, by the nucleon number is equal to 545 times point 3 mass uh, electron volume by 62. So the 62 here is the mass number of nickel, or 8.795 mass electron volume per nucleon. So to evaluate a result means that it would take a minimum of 545.3 mass electron volume to pull a uh, nickel completely apart into 28 protons and 34 neutrons. The mass defect of nickel is about 1% of the atomic mass. So the binding energy is therefore about 1% of the rest energy of the nucleus, and the binding energy per nucleon is about 1% of the rest energy of a nucleon. Note that the mass defect is more than half the mass of a nucleon, which suggests how tightly bound nuclei are. So our next topic is the nuclear force. So the force that binds protons and neutrons together in the nucleus. Despite the electrical repulsion of the protons, is an example of strong interaction. In the context of nuclear structure, this interaction is called the nuclear force. So we have a some model, which is the liquid drop model. It suggests that by observation that all nuclei have nearly the same density. The individual nucleons are analogous to molecules of a liquid held together by the short range interaction and surface tension effects. So we have the second model, the shell model. It accounts for many features of nuclear energy levels. According to this model, the motion of each nucleon is governed by the average attractive force of all the other nucleons. So the resulting orbits form shells, such as the orbits of electron in atoms do. As nucleons are added to the nucleus, they drop into the lowest energy shell permitted by the Pauli principle, which requires that each nucleon have a unique set of quantum numbers to describe its motion. So we have here next one is the nuclear stability and radioactivity. Among about 2,500 nuclei, fewer than 300 are stable. The others are unstable structures that decay to form other nuclides by emitting particles and electromagnetic radiation, a process called radioactivity. Alpha decay. Radioactive nuclides are not stable but decay into other nuclides. When unstable nuclides decay enter different nuclides, they usually emit alpha or beta particles. An alpha particle is a helium nucleus, two protons and two neutrons bound together with a total spin 0. Alpha decay is possible whenever the mass of the energy and neutral atom is greater than the sum of the masses of the final neutron atom and neutral helium 4 atom. Then beta decay has three types of decay. decay, which is the beta minus decay that can occur whenever the mass of the original neutron atom is larger than that of the final atom. Beta plus decay can occur whenever the mass of the original neutral atom is at least 2 electron masses larger than that of the final atom. Electron capture can occur whenever the mass of the original neutral atom is larger than that of the final atom. So that is a beta decay. Three types of beta decay, and we have here the gamma decay. In both alpha and beta decay, the Z value of nucleus changes. The nucleus of one element becomes the nucleus of a different element. In gamma decay, the element does not change. The nucleus merely goes from an excited state to a less excited state. So we have here the spontaneous emission, mass, and charge are conserved. So in alpha emission, we have uranium with a mass number of 238 and atomic number of 92. Proceed to thorium, which has 234 mass number and 90 atomic number, plus helium with 4 mass number and 2 atomic number. In beta emission, we have the iodine with 131 mass number and 53 atomic number. Process to xenon with 131 mass number and 54 atomic number, plus 2 electron with 0 mass number and -1 atomic number, and also connect to the neutron with 1 mass number and 0 atomic number. Process to protons with 1 mass number and 1 atomic number, plus electron with 0 0 0 mass number and -1 atomic number. So in gamma emission, this will be simplified as gamma gamma with 0 atomic 0 atomic mass and atomic 0 mass number. So in positron emission, we have carbon with a mass number of 11 and atomic number of 6, and boron with 11 carbon no 11 mass number and 5 atomic number, plus electron with 0 atomic with 0 mass number and 1 atomic number. Then proton with 1 mass number and 1 atomic number, and neutron with 1 mass number and 0 atomic number, plus electron with 0 mass number and 1 electron 1 atomic number. In the electron capture, we have proton with 1 mass number and 1 atomic number, plus electron added up with electron with 0 mass number and -1 atomic number, then neutron with 1 mass number and 0 atomic number. So, in natural radioactivity, the study of natural radioactivity began in 1896, 1 year after Roentgen discovered X-rays. Intensive investigation followed that revealed the emission consists of positively and negatively charged particle and neutral rays. They were given the names alpha, beta, and gamma. So in its application, earthquake can cause in part by radioactive decay of uranium in the Earth's interior. These decays release energy that helps to produce convection currents in Earth's interior. Such current drive the motion of Earth's crust, including the sudden sharp motion that we call earthquake. So the next one is the activities and half-lives. So radioactive decay rates. So we have here neutron number n, neutron number, then by time is equal to uh, this is the number of radioactive nuclei in sample at time. Then the negative quantity, which is the dn, change in that number during short interval. Then this is uh, the formula, which is the negative quantity by time divided by the um, decay rate is equal to decay constant, neutral number, and the time. So in example for 3.8, the isotope cobalt decay by electron capture of 2 iron with a half-life of 272 D. The iron nucleus is produced in an excited state, and it almost instantaneously emits gamma rays that we can detect. So find the lifetime and decay constant for cobalt. If the activity of a cobalt radiation source is now 2.00 no uh, uh, psi, how many cobalt nuclei does the source contain? Then what will be the activity after 1 year? So the solution this problem uses the relationship among the decay constant, lifetime T mean, and activity negative quantity uh, over time by decay rate. In part A, we use equation to find decay constant and T min from P over 1/2. In part B, uh, we use equation 43.16 to calculate the number of nuclei, neutron number by time from the activity. Finally, in part C, we use equation 43.16 and 43.17 to find the activity after 1 year. So, to execute A, it's convenient to convert the half-life to seconds to T, 1/2. The 1/2 is equal to 272D, 272D by 86,400 100 SD is equal to 2.35 times 10 raised to the power of 7 S. So the mean lifetime and decay constant, or T mean, is equal to T 1/2 over 1 and 2 is equal to 2.35 multiplied by 10 raised to the power 7s over 0.693, and equal to 3.39 times 10 raised to the power of 7s is uh is equal to 392 days. So the decay constant is equal to 1 over T min. So this means this is equal to 2.95 times 10 raised to the power of negative 8 as uh, raised to the power of negative 8 as negative 1. In the B, the activity negative quantity time over decay rate is given as 2.00 mu size. So the negative uh, so the given is equal to 2.00 times 10 raised to the power of negative 6 by 3.70 times 10 raised to the power of 10 as negative 1, and this is equal to 7.40 times 10 raised to the power of 4 decays. So from the equation, this is equal to decay constant neutron star and neutron number time. So we find neutron number by time to negative uh, negative quantity by time uh, over decay rate over decay constant is equal to 7.40 times 10 raised to the power 4 as negative 1 over 2.25 times 10 raised to the power of negative 8 as negative 1. And this is equal to 2.51 times 10 raised to the power of 12 nuclei. So if you feel where we're being careful about the units decays and nuclei, you can use decay or over nucleus by s as the unit for decay constant. So in C equation, number the number neutron number by time of nuclei remaining after 1 year is 1 year 3 is equivalent to 3.156 times 10 raised to the power 7 as is neutron number by time is equal to uh, neutron number uh, neutron number electron raised to the power uh, of negative decay constant by time is equal to neutron number, and it's electron number electron, and decay constant is negative 2.95 times 10 raised to the power of negative 8 as negative 1, and its time is 3.156 times 10 raised to the power of 7s. So all in all is equal to 0.394 neutron star number. So the number of nuclei has decreased to 0.394 of the original number. Equation for the In the equation says that the activity is proportional to uh, to the number of nuclei. So the activity has decreased by this same factor, 2 um, open parenthesis 0.394 by 2.00 MOSI, close parenthesis, is equal to 0.7788. So the number of nuclei found in the part B is equivalent to 4.17 by 10 raised to the power of negative 12 mole with a mass of 2.3810 38 by 10 raised to the power of negative 10 grams. This is a far smaller mass than even most sensitive balance can measure. After 272-day half-life, the number of cobalt nuclei has decreased to neutron number over 2 after 2 by 272. Decay is equal to 544 decay. It has decreased to neutron number 2 cube, 2 squared is equal to neutron number over 4. This result agrees with our answer to part C, which says that after 365 days, the number of the nuclei is between neutron number 2 and neutron number 4. So note, the decay constant has different values for different nucleides. The half-life T 1/2 team required for the number of radioactive nuclei to decrease to 1/2 the original number. Radioactive dating is an application of radioactivity is the dating of archaeological and geological specimens by measuring the concentration of radioactive isotopes. The most familiar example is carbon dating.
So going back to the radioactive decay rates, so we let the NT, which is the number of radioactive nuclei in sample at time, and the DNT, which is negative, it is the change in that number during the short interval, the DT. So thus we have the negative change in that number during the short interval over the short interval is directly proportional to the lambda times the number of radioactive nuclei in the sample at time. So we should note that lambda is equivalent to the decay constant and has different values for different nuclides. So half-life, represented by the letter T and 1/2, is the time required for the number of radioactive nuclei to decrease to 1/2 the original number. And then we have the radioactive dating. So, radioactive dating is the application of radioactivity, and it is the dating of archaeological and geological specimens by measuring the concentration of radioactive isotopes. So, the most familiar example is the carbon dating. So, a half-life may not be enough, so it is sometimes implied that any radioactive sample will be safe after a half-life has passed, but that's wrong. If your radioactive waste initially has 10 times too much activity for safety, it is not safe after one half-life. So, when it still has 5 times too much, even after 3 half-lives, it still has 25% more activity than is safe. So the number of radioactive nuclei and the activity approach zero only approaches infinity. So a common unit of activity is the Curie. So it is abbreviated as the CI, which is defined to be the case per second. So this is approximately equal to the activity of 1 gram of radium. So the SI unit of activity is the becquerel. So it is abbreviated BQ. So 1 becquerel is 1 decay per second. So it is equivalent to, the 1 CI is equivalent to 3.70 times 10 raised to the power of 10 decays per seconds. So in becquerel, it is also 3.70 times 10 raised to the power of 10 decays per second. So let's take this example from the book. So what we are doing now is the radiocarbon dating. So before 1900s, the activity per unit per mass of atmospheric carbon due to the presence of carbon-14 average about 0.255 becquerel per gram of carbon. So what fraction of carbon atoms were carbon-14? So in analyzing an archaeological specimen containing 500 milligram of carbon, you observe 174 decays in 1 hour. What is the age of the specimen, assuming that its activity per unit mass of carbon when it died was that average value of the air? So the key idea is that the present day activity of biological sample containing carbon-14 is related to both the elapsed time since it stopped taking it in atmospheric carbon and its activity at that time. So to solve for the age of the specimen, in part A, we determine the number of carbon-14 atoms from the activity. So we find the total number of carbon atoms in 500 milligram by using the molar mass of carbon, which is at 12.011 grams per mole. So, and we use the result to calculate the fraction of carbon atoms that are carbon-14. So the activity decays at the same rate as the number of carbon-14 nuclei. After the identify and set up, we should do the execute. So for A, we must first find the decay constant. So the half-life is equivalent to the 5,730 years and equal to 5,730 years times the lambda, which is the decay constant for the carbon-14, which is the 3.156 times 10 raised to the power of 7. And then it is then equal to 1.808 times 10 raised to the power of 11 seconds. So lambda is equivalent to logarithm times 2 over the half-life. Then equivalent to logarithm times 2 is equivalent to 0.693 over the half-life, which is 1.0808 times 10 raised to the power of 11 seconds. Then the lambda, then the decay constant is equivalent to 3.83 times 10 raised to the power of negative 12 seconds. So then from this, we should find the number of remaining nuclei, the NT, which is the negative change in that number during the short interval over the interval over lambda. So it is then equal to the 0, as we have known that the activity per unit per mass of atmospheric carbon due to the presence of carbon-14 in 1900s is about 0.255 becquerel. So 0.255 seconds over that decay constant. So 3.83 times 10 raised to the power of negative 12. Then the result will be the 6.65 times 10 raised to the power of 10 atoms. So the total number of carbon atoms in 1 gram, 1 over 12.011 mole, is 1 over 12.011 times the remaining nuclei, the 6.022 times 10 raised to the power of 23. So, the result will be the 5.01 times 10 raised to the power of 22. The ratio of carbon-14 atoms to the carbon atom is 6.55 times 10 raised to the power of 10 over the 5.01 times 10 raised to the power of 22 is equal to the 1.33 times 10 raised to the power of negative 12. So, 1.33 times 10 raised to the power of negative 12 is the ratio of carbon-14 atoms to all the carbon atoms. So, only 4 carbon atoms in every 3 times 10 raised to the power of 12 are carbon-14. So, let it be assuming that the activity per gram of the carbon in the specimen when it died was 0.255 becquerel per gram. So, the activity of 500 milligrams of carbon was then 0.500 grams times 9.8 H times G is equals to 459 H. So, the observed activity now at time is 174 H. So, 174 decays. Since the activity is proportional to the number of radioactive nuclei, the activity ratio then is 174 over 459. So, it is the result will be 0.379 equals to the number ratio. So, now we solve the time and insert values for the remaining nuclei and NO and the lambda. So, T is equals to logarithm plus the number of radioactive nuclei in the sample at time over the NO over the negative lambda or the decay constant. So, it is then equal to the logarithm 0.379 over the negative 3.83 times 10 raised to the power of negative 12. Then the result will be 253 times 10 raised to the power of 11 seconds, or equivalent 11s, equivalent to 8,020 years. So, after 8,020 years, the carbon-14 activity has decreased from 459 to 174 decays per hour. So, the specimen died and stopped taking carbon dioxide out of the air about 8,000 years ago. So, that is some problem of the carbon dating and how to solve the carbon dating. Next is we proceed to the biological effects of radiation. So, we should know how to calculate the radiation doses. So, what is this radiation doses? Radiation dosimetry is the quantitative description of the effect of radiation on living tissue. So, the absorbed dose of radiation is defined as the energy delivered to the tissue per unit per mass. So, it is equivalent to 1 rad is equals to 0.01 joules per kilogram and or equal to the 0.01 gray. So, the gray is the SI unit for the radiation doses. The absorbed dose of radiation. So, we have also the RBE or the relative biological effectiveness, also called the quality factor variation of specific variation of specific radiation. So, the biological effect described by RBE or the relative biological effectiveness times the gray, and the SI unit of equivalent dose for humans is the sievert, which is represented by the letters S and V. So, the equivalent dose for humans is equal to the SV equal to RBE times the gray. So, this table shows the relative biological effectiveness for several types of radiation. So, from the X-rays and gamma rays, the RBE is equals to 1, the electrons 1.0 to 1.5, the slow neutrons 3 to 5, the protons 10, the alpha particles 20, and the heavy ions is 20. So this graph shows the contribution of various sources to the U.S. average radiation exposure in the U.S. population. So as expressed as percentages in the total. So from human activity. So from cosmic is 8%, terrestrial 8%, the internal 11%, and the radon, the element radon is 55%, a nuclear medicine, the 4%, and medical x-rays, 11%. So, the natural activity, radiation exposure is 82%. So, from human activity, it is only 18%. So, let's take this example and how to calculate the dose from a medical x-ray. So during a diagnostic x-ray examination, a 1.2 kilogram portion of a broken leg receives an equivalent dose of 0.40 millisievert. So what is the equivalent dose in millirem? What is the absorbed dose in millirad and in milligray? So, if the X-ray energy is 50 kilo electron volts, how many X-ray photons are absorbed? So, identify and set up. We are asked to relate the equivalent dose, the biological effect of the radiation, measured in sieverts or rems, to the absorbed dose. So, the energy absorbed per mass, measured in grays or rads. So in part A, we use the conversion factor. 1 rem is equivalent to 0.01 sievert for equivalent dose. So we have seen earlier the table for 43.3 that gives the RVE for X-rays. So we use this value in part B to determine the absorbed dose. So, and finally, in part C, we use the mass and definition of absorbed dose to find the total energy absorbed and the total number of photons absorbed. So, for problem A, the equivalent dose in MR and millirem. So, we have given the equivalent dose. We have given that the 1.2 kilogram portion of broken leg receives an equivalent dose of 0.40 millisievert, and we will divide it by the 0.1 sievert over the REM because the problem is that what is the equivalent dose in millirem. So the result will be the 40 millirem. For letter B, for X-rays, the RBE is equivalent to 1 rem over rad or 1 SB over gray. So the absorbed dose is 40 millirem over 1 rem over rad and is equivalent to 40 millirad. So 0.40 millisievert over 1 sievert over G gray is equivalent to 0.40 milligray or equivalent to 4.0 times 10 raised to the power of negative 4 joules per kilogram. So the total energy absorbed is from the answer above, the 4.0 times 10 raised to the power of 4 joules per kilogram times 1.2 kilogram. So it is then equals to the 4.8 times 10 raised to the power of negative 4 joules equals to 3.0 times 10 raised to the power of 15 electron volts. So the number of X-ray photons is 3.0 times 10 raised to the power of 15 electron volts over 5.0 times 10 raised to the power of 4 electron volts per photons. So the result will be 6.0 times 10 raised to the power of 10 photons. So the absorbed dose is relatively large because X-rays have a low RBE. If the ionizing radiation had been a beam of alpha particles for which RBE is equals to 20, the absorbed dose needed for an equivalent dose of 0.40 millisievert would be only 0.020 milligray, corresponding to a similar total absorbed energy of 2.4 times 10 raised to the power of negative 5 joules. So after knowing the radiation hazard and how to calculate the radiation doses, we should know about the beneficial uses of radiation. So what are these? The radiation is widely used in medicine for intentional selective destruction of tissue such as tumors. Radioactive isotopes have virtually the same electron configuration and resulting chemical behavior as stable isotopes of the same element. So, but the location and concentration of radioactive isotopes can be easily detected by measurements of the radiation they emit. And there are many direct effects of radiation that are also useful, such as strengthening polymers by cross-linking, sterilizing surgical tools, dispersing of unwanted electricity in the air, and laundry detergent manufacturers have even tested the effectiveness of their products using radioactive dirt. So, also, the gamma rays are also being used to sterilize and preserve some food products. What and this there is this autoradiography. So what is this autoradiography? Autoradiography is an imaging technique that uses radioactive sources contained within the exposed sample. In vitro autoradiography methods involve the isolations of cellular components such as DNA, RNA, proteins, or lipids, and followed by labeling with suitable radioisotopes. So either using the gamma camera, a scanning detector used to produce image, or scintigram that reveals which part of the body take up these gamma-emitting molecules. And this technique, in which the technetium-99 acts a radioactive tracer. So there are a lot of elements that are used as a radioactive tracer. Then this element, the technetium-99 that acts as a radioactive tracer, plays an important role in locating cancers, embolism, and other pathologies. And next is the nuclear reaction. So, reaction energy is the difference between the masses before and after reaction. So, there are two types of reaction, which is the exergic reaction and the endoergic reaction. So, this exergic reaction, when the Q, the reaction energy, is positive, the total mass decreases and the total kinetic energy increases. While the endoergic reaction, when Q is negative, the mass increases and the kinetic energy decreases. But it cannot occur at all unless the initial kinetic in the center of mass reference frame is at least as great as the reaction energy. So the threshold energy is the minimum kinetic energy to make an endoergic reaction. Reaction go. So what is a neutron absorption? So it is when a heavy nuclei bombarded by neutrons can undergo a series of neutron absorptions, alternating with beta decays in which the mass number increases by as much as 25. So let's take this example 43.11 for the exergic and endoergic reactions. For one, when a lithium-7 nucleus is bombarded by a proton, then 2 alpha particles, the helium-4, are produced. So find the reaction energy. And letter B, calculate the reaction energy for the reaction. Helium-4 reacts with nitrogen-14 and yield to oxygen-17 plus hydrogen-1. So the reaction energy for any nuclear reaction equals to C squared times the difference between the initial mass and the total final mass. So for letter A, we should execute the reaction for hydrogen-1 that reacts to lithium-7 will yield to 2 alpha particles, the helium-4, and then the initial and final masses in the respective sums. So the resulting Mass for this from the hydrogen 1 reaction and lithium 7 is the 8.02 U. And the two alpha particles, the helium 4, the total mass is 8.0 U. So the mass decreases by 0.018623 U. So the reaction energy is Q is equal to the 0.018623 U times 931.5 mega electron volts over U. And then equals to, the result will be the positive 17.35 mega electron volts. And that is the reaction energy when a lithium-7 nucleus is bombarded by a proton. Then two alpha particles are produced. And for letter B, the initial and final masses are the helium-4 reacts with nitrogen-14. The initial mass is the 18.00 U, and for the yield, which is the oxygen-17 and the hydrogen-1, is that it is the 18.006957 U. So the mass increases by 0.001280 U, and the corresponding reaction energy is Q is equals to the negative 0.001280 U times 931.5 mega electron volts over U. So the result will be negative 1.192 mega electron volts. So the reaction in part A is exergic. So as we have known earlier that the exergic reaction is when Q is positive, the total mass decreases and the total kinetic energy increases. So the final total kinetic energy of the two separating alpha particles is 17.35 mega electron volts, and it is greater than the initial total kinetic energy of the proton and the lithium nucleus. So the reaction in part B is endoergic. So endoergic reaction is when Q is negative, the mass increases and the kinetic energy decreases. So in the center of mass system, that is in a head-on collision with zero total momentum, the minimum total kinetic energy, total initial kinetic energy required for this reaction to occur is 1.192 mega electron volts. So we will proceed to the nuclear fission. And nuclear fission is a decay process in which an unstable nucleus splits into two fragments of comparable mass. So fission resulting from neutron absorption is called induced fission. So the fission reactions, it may seem to be violation of conservation of energy to have an increase in both the binding energy and the kinetic energy during the fission reaction. But relative to the total rest energy of the separated nucleons, the rest energy of nucleus is EO minus the binding energy. Thus, an increase in binding energy corresponds to a decrease in the rest energy, and it is converted to the kinetic energy of the fission fragments. So, nuclear reactions, it is a system in which a controlled nuclear chain reaction is used to liberate energy. So for example, in nuclear power plant, this energy is used to generate steam, which operates a turbine and turn an electrical generator. So we have this image, a liquid drop model of fission. This is to show how the nuclear fission happens. So from a uranium-235 nucleus absorb a neutron. So, to letter B, so the resulting is the uranium-236. So, from uranium-235 to uranium-236, nucleus is in highly excited state and oscillates strongly. So ni oscillates na siya, and to letter C, a neck develops and electric repulsion pushes the two lobes apart. So this oscillation encourage for a neck to develop. So the electric repulsion and pushes the two lobes apart and will result to the letter D. The two lobes separate, forming fission fragments. So the fragments emit neutrons, and the time of fission, or occasionally a few seconds later. So the fission fragments then develop. So that's how the nuclear fission happens. So this is a schematic diagram of a nuclear fission chain reaction from first generation neutron and will result to the fourth generation neutrons. So it is also a schematic diagram of a turbine. So from the control rods, reactor core, the moderator, and the hot water pump the water to cool reactor pressure, which is the primary loop, and the secondary loop is the water high pressure. It will create a electrical generator. So let's take this example problem 43.12 from the book. So uranium consumption in nuclear reactor. So what mass of uranium-235 must undergo fission each day to provide 3,000 megawatts of thermal power? So identify and set up fission of uranium-235 liberates about 200 mega electron volts per atom. So we use this and the mass of the uranium-235 atom to determine the required amount of uranium. So let's execute. Each second, we need 3,000 megajoules, or 3,000 times 10 raised to the power of 10 joules. So each fission provides 200 mega electron volts, or 200 mega electron volts per fission, times 1.6 times 10 raised to the power of negative 13 joules per mega electron volts. And the result will be 3.2 times 10 raised to the power of negative 11 joules per fission. So the number of fissions needed each seconds is 3,000 times 10 raised to the power of 6 joules over 3.2 times 10 raised to the power of negative 11 joules per fission. So the result will be 9.4 times 10 raised to the power of 19 fissions. So each uranium-235 atoms has a mass of 235 U times 1.66 times 10 raised to the power of negative 27 kilogram per U, and the result will be 3.9 times 10 raised to the power of negative 25 kilograms. So the mass of uranium-235 that undergoes fission each seconds is 9.4 times 10 raised to the power of 19 times 3.9 times 10 raised to the power of negative 25 kilograms. So the result will be 3.7 times 10 raised to the power of negative 5 kilogram, and it is equivalent to 37 microgram. So in one day, there are 86,400 seconds. So the total consumption of uranium-235 is 3.7 times 10 raised to the power of negative 5 kilograms per seconds times 86,400 seconds, and the result will be 3.2 kilograms. So for comparison, we should evaluate a 1,000 megawatts coal-fired power plant burns 10,600 tons, about 10 million kilograms of coal per day. After the nuclear fission, we should also know about the nuclear fusion. So if the nuclear fission decay process in which an unstable nucleus splits into two fragments of comparable mass, then nuclear fission is different. It is a two or more small light nuclei come together or fuse to form a larger nucleus. So, and then it occur only at extremely high temperature in the sun, and these temperatures are formed only deep within the interior. So, hence the sun cannot fuse all of its protons and can sustain fusion for a total of only about 10 billion years in total. So, as we have known that the age of the sun is 4.5 billion years. So, the sun is about halfway through its available store of protons. So, this is the proton-proton chain. So, from the number 1, the two protons combine to form a deuteron, which is the hydrogen 2. Then, in the 2, the second process, as well as the positron, the beta plus, and the electron neutrino. So, from the third, a third proton combines with the deuteron, forming a helium nucleus, which is the helium-3 and emitting a gamma-ray photon. So, 2 helium-3 nuclei fuse, forming a helium-4 nucleus and releasing 2 protons. So, this is a proton-proton chain that shows how the nuclear fusion happened. So, the energy as starlight comes from fusion reactions deep within a star's interior. So, when a star, as we have known that the nuclear fusion only occur at extremely high temperature, and this temperature are found only deep within the interior. So the starlight comes from the fusion reactions deep within a star's interior. When a star is first formed and for most of its life, it converts the hydrogen in its core into helium. And as a star ages, the core temperature can become high enough for additional fusion reactions that convert helium into carbon, oxygen, and other elements. So let's take this example 43.13, which is a fusion reaction. So there are two deuterons fused to form a triton. So this triton is a nucleus of tritium or hydrogen 3 and a proton. So how much energy is liberated? So this is a nuclear reaction of the type discussed in section 43.6. So execute. Adding 1 electron to each nucleus makes each neutral atom. So we find that energy Q is equals to 2 times 2.01 U minus 3.01 U minus 1.007825 U. And then times 2 the 931.5 mega electron volts over U, and then the result will be 4.03 mega electron volts. So thus the 4.03 mega electron volts is released in the reaction, and the triton and proton together have 4.03 mega electron volts, have more kinetic energy than the two deuterons had together. And that's the end of our video. I hope you enjoy and learn something from it, and thank you for watching.